Hello everybody and welcome to SkyTour live stream. It is I, your host, Mark D'Antonio, and I'm here with a crowd. Say hello! Woohoo! We are at Contact in the desert for 2023, and we are at a wonderful resort, the Renaissance Resort. I've got a ton of people here from all over the country. Actually, some people from out of the country. If you're from England, raise your hand. Right here. Yeah, you were in my lecture. That's right. Yeah, so I'm very happy to see everybody here tonight. And what we're doing is we're going to go perusing the skies. Now, we're perusing the sky from California, but we're running the telescope that's 300 miles away in Arizona. Normally when we do this, I'm in Connecticut, and the telescope is 2,500 miles away. And when it's raining or snowy in Connecticut, I can run this telescope and we get to see some beautiful sights from Arizona, because we have 300 clear nights a year. I don't get a lot of sleep, right? So what we're going to do is start off right away with just a little tour so you can see exactly where we're going. If you look on the screen here that you are all seeing, the screen that our wonderful people, and I see in our chat, we've got lots of people showing up. Okay, we have Sam S. and Daryl's with us. Daryl's actually my co-host. And I didn't get the Skype thing figured out here, so he's stuck in the chat tonight. So say hi, Daryl. Hi, Daryl. There you go, Daryl. You got to hear them say hello to you. And then we have some wonderful people here. We have a bunch of regulars. We have, we have Terry Haig. We have Marianne. Marianne, what are you doing in here? You're watching it live. Marianne is sitting right here in the yeah, she just wanted to hear her name. That's right, I heard that. Yeah, and we're gonna get a lot of people in here tonight, so it'll be kind of fun to watch. Now we focused the telescope, and we're ready to go take a hike to go look at some other things. But I wanted to share with you a way in which we actually do that. So what I'm gonna do is find my cursor. It's here somewhere. There it is. And I'm going to come down here. It's hooked up to the telescope so that when I want to go someplace, all I have to do is tell it where to go, and I can do it in the planetarium. So right now what I've done in this program is I've told it to go to Measure 101, a spiral galaxy. All right, and this spiral galaxy is 20 million light years away. And at 20 million light years away, it means that the light getting to your eyes took 20 million years to get here. Now, recently there was a supernova in M101, and tonight I went to look for it, and guess what? It's already faded away. All right, but you know what? It's okay, because I'm going to show it to you anyway. All right, so we come back here, all right, and what I'm going to do, again, I go to these very important parameters right here, and these parameters, of course, are the exposure and the gain. So now what we're going to do is take the exposure, and we're going to go to 25 seconds. All right, now we have a full moon out, so we have filters to help mitigate that, which is kind of cool. All right, and then we're actually going to come over here, make a little adjustment. I'm getting seasick from the screen. There we go. So I'm going to come out of night vision mode, and we are going to start counting up. Down here, down at the bottom of the screen, right here, come all the way down, so right there, you see a progress bar, that yellow bar. We're taking a 25-second exposure, and the telescope is guiding itself. We have a special guider on the telescope that automatically follows the stars properly and accurately. And so if I then come in and live stack this, okay, we will see a galaxy. Now, that doesn't look so good. Let me fix that for you. Let's actually get a little bit more contrast here. All right. What do you think? Right, isn't that beautiful? And this is what I do every day. Can you imagine? And I'll tell you right now, I never get tired of this. This is live astronomy. This is the universe live in real time. You gotta imagine that that's something. And by the way, think about it. The light you're seeing from that galaxy right there, oh wait, the supernova's still there. Yeah, it's right there, that little red dot. See, what happens is a supernova starts off very, very hot and bright, okay? And when it starts off very, very hot and bright, it's going to be blue. But then over time, what happens is it gets cooler. And in the world of light and astronomy, cooler means redder. So it turns more red. What do you think, huh? And you're seeing it live. And the funny thing is, you might be the only ones on Earth looking at this right now, because there might not be another telescope looking at it right now. So you guys are seeing something that might be fleeting. The light coming took 20 million years to get here. And the light that you're seeing right there is the light that comes and goes. It's gone forever after that. Isn't that something? Actually, very good question. Is that in the Milky Way galaxy? No. This galaxy is its own Milky Way. You're seeing, see all the separate stars you see in the image here? All those stars are here in the foreground. This galaxy is 20 million light years past all that. Our galaxy is 100,000 light years across. That's 20 million light years away. So you're actually looking through a veil of stars, literally in front of your cosmic face, at something far away in Connecticut, for instance. So that's the kind of, actually even way further. So that's kind of the distance we're talking about, you know. Now in my book, The Populated Universe that I wrote, we talk about cosmic distance scales and so forth, but it's written in a way you can all understand. It's very important. I have a few of these books left in there, so if you want to buy one, I'm here tomorrow, whatever. Okay, this is not a sales pitch, but if you're interested, the book actually answers a question. When you are asked, do you believe there's life elsewhere? Raise your hands if you think there is. Every hand's going up. Okay. Well, he just didn't put his hand up. Oh, he's asleep. Sorry. Just kidding. No, but every hand goes up. So the question becomes, if you believe in life elsewhere, then the next question is, why? What makes you think we're not alone? And then you answer, well, I just think we're not alone. I can't believe we'd be alone with all the planets they found out there. And that's kind of where it ends for you, because you don't really have anything else to throw in. The book answers all that for you. It tells you things like, we're carbon-based beings. We're bilaterally symmetric, the same on the left, same on the right. Maybe due to the way DNA replicates. And DNA is found in almost every living thing on this planet. Okay? So isn't it possible that all of those characteristics that make us what we are and make every animal what it is are templates that are just automatically provided by the universe? Carbon is the fourth most abundant element in the entire universe, and then you're made of a whole bunch of it. Oxygen is the third most abundant, even more. And carbon and oxygen are like this. They're inseparable. They belong together. They work together. They need each other to survive as a life form. So, our universe is vast. But if you're an alien species and you're looking for another planet like yours, and you're in that galaxy right there, what do you think you're going to do? Well, you're right. Okay, sure. But let's pretend that you have the capability to look for anything you wanted to find out there in the galaxy. What you look for is oxygen, because you need oxygen as a life form. And guess what? We're doing that too with the James Webb Space Telescope. We are looking for oxygen around other stars, around the planets, or in the atmospheres of those planets. And anybody that does that, anyone else that is going to be looking for life, any other species, if they're carbon-based, they're going to look for oxygen too. So guess what? 2.5 billion years ago, that's when our story started in terms of oxygen, that's when phytoplankton started producing oxygen. And the oxygen is a waste product. So yes, you're kind of breathing bacteria poop. Well, hey, go figure. If it keeps you alive, don't argue, right? But think about this. 2.5 billion years ago, the oxygen signal in our atmosphere started leaving our planet for all to see. Stephen Hawking said, famously, we should stay low, we should stay out of the line of fire, don't let aliens know we're there, right? Remember that?
Yeah.
Too late. Oops. We broadcast the oxygen signal 2.5 billion years ago when it started to build up. And that's, unfortunately, or fortunately, why any alien race looking anywhere in the universe for life like itself or life that uses oxygen as we do, bless you squared, okay, will actually find oxygen in our atmosphere. Say, hey, there's a big blue bundle of a planet over there, right? And Carl Sagan famously said that we are a pale blue dot. Okay, my favorite astronomer. What can I say? All right. And Carl Sagan said that because we are a pale blue dot, but our oxygen is visible for millions of light years out there. Actually, this is 20 million light years away. It's entirely possible that a civilization with the technology is looking at us from there right now. True. Yeah. And if that's true, you know what that means? It means that there's a civilization out there that says, hey, there's someone like us out there maybe. Let's get in our intergalactic ships and go visit them. It might take them 1 million years to get here. But what if they left 2 million years ago? They've been here for 1 million years. So you see, and the universe is a time machine. Every single star you see in this image, every single star, that one, that one, that one, that one, and that galaxy, they're all time machines. We're seeing them at different times in their life. Okay? If this star is, say, 50 light years away, and this star here is 10, okay, then you're seeing them as they were 50 years ago and 10 years ago. Everyone is different. The universe is all 3D. You get that? That's a cool thing, isn't it? This is a time machine over your head. The sun is 8 minutes old. If the sun went out on a sunny day while you're on the beach, you wouldn't know it for 8 minutes. And then it goes out. And like, who the heck turned off the sun? Some force greater than us, that's for sure. All right, so what I'm doing right now, you'll notice all this complexity. This is called a stack. We actually have stacked, let me see. We have stacked we've stacked a bunch of images here. And what happens is I'm making an image sandwich. I take the first one, then I take a second one, align it with the first, put it on top. Do that third, fourth, fifth, all the way up till we get to as high as we want to go. And it makes it makes it a little clearer as we go. In this particular case, I think that with the moon out, stacking doesn't always work 100%. And so we might have that problem with this, but it's not a big deal. I'm going to come back in here for a second. And I'm going to, oh, and by the way, you're hearing our music, by the way. We have some really nice music. The iPod music, just a minute here. There we go. That might be a little loud. See, because I think it should be a production. I think that if you're going to be in here, if I'm not going to talk for like 10, 20 seconds for something, be entertained by music, right? Yeah, and as long as I keep talking in the mic, you won't say that the music's drowning me out. You know, but that does happen from time to time. So, let's keep going here. There it is. All right. So what you haven't seen is the actual movement of the telescope, and I'd like to show you that too, because that's also pretty cool. All right, so let's get down here, and I'm going to turn off the operations camera because it's not able to see me right now. Okay. All right, let's see. We stacked 7 and we skipped a bunch, and that has to do probably with the nature of the moon's brightness. I'm going to increase our. Oh, I got our gain up pretty high. This is good. All right. So anyway, for one thing, do you see the spiral arms in this galaxy? See those spiral arms? You see those, right? I'm gonna find where I just put my glasses. Okay. Here they are. Okay, so a galaxy has these spiral arms like this. See those? And again, you've seen this all live. So you see the spiral arm here, a spiral arm there. spiral arm there. Okay, the spiral arms are where the stars form. That's where the new stars are forming. And the old stars tend to cluster in the middle, all right? That's why they look yellow. The new stars are hot and blue and young. Hot and blue. Hot. Hot, blue, and young. That's right, right? Like, I'm hot, blue, and young. Ew. So yeah, but in stars, that's attractive. Okay? So, you know, what can I say? But there are little red stars. Okay? We have stars that go from hot and blue to very, very cool and red. Right? And we have a mnemonic we use, which I learned, which I never really liked fully, but it goes O, B, A, F, G, K, M. Those are the letters. O stars are very hot and blue. B's are hot and blue, but less so than the O's. The A stars are white. The F stars are starting to be whitish yellow. The G stars, like our own, is sort of a yellowy white star. And then you have the K stars, which are more orange, and the M stars, which are red. And the temperatures go down all the way through the gamut. And these, the mnemonic we used and learned, and you have to imagine a professor saying this to a class. Oh, be a fine girl, kiss me. O, B, A, F, G, K, M. Right?
It's like Mary's violet eyes make Johnny stay up nights proposing the planets.
Oh, there you go. Right. That's right. That's right. And the proposing part of that statement that you just said, I think Pluto's a planet. Are you with me?
Yeah.
All right.
She keeps getting demoted and brought back and kicked
Yeah.
out.
I met Clyde Tombaugh, the founder of Pluto, and I sat with him on a grassy knoll in Vermont, and we had a conversation about Pluto. That man was the sweetest guy on planet Earth. A very small guy, very soft-spoken, and he talked about the discovery, and he lit up when he talked about it. What do you think he'd think if they said, we don't give you a planet anymore, Clyde? Clyde doesn't get a planet anymore? I don't think so. So anyway, oh yeah. So, we'll revisit this here shortly, but what I'm going to do is take you to the next level here. All right. So if we want to check out something different, what we'll do is go and do this. Let's see. Oh, let me look up there. Right, oh, I know what to do. You'll like this. What's that?
Do you ever see anything moving out there?
And the spiral galaxy?
Oh, no, you know why? Because they're so far away. The question was for the folks listening in around the world, do we ever see anything moving when we're doing this? And when we look at galaxies and even stars in our galaxy, the universe is so vast, the stars are so far apart from each other in general, that we don't see actual movement except over many months. Now, we've done that. We have created shots where we have seen stars moving over time, because they do move, right? But usually when there's comets out there, we can see comets moving in the space of a few minutes. So we can watch a comet moving from, say, one corner of the screen to the other over the course of an hour and a half. And then what we do before you even leave the stream is we animate it and show you the whole thing from start to finish. Okay, and that's usually done by our Bulgaria friend that lives in Sofia, Bulgaria. Her name is Izabela. She's an artist, and she just loves SkyTour Livestream. So she will put together a montage showing the motions across the sky in the time that we've been doing the stream. You know, we also do mosaics, where we do more than one shot showing all parts around something, and then she'll mosaic those together for us before we're even done. I can do it, but I'm in the middle of a stream. But she does it, and it's great, you know. So what we're going to do now is we're going to go to a new cluster, a different cluster, and we're going to tell a telescope to go there. But before I do that, I'm going to come back in here, and I'm going to get rid of the stack and go back into our night vision mode. Okay, so you'll see that I'm going to go back down to 1 second timing here.
What's wrong with your audio?
What's wrong? Oh, I know, I hear that.
Is
I
that
don't know.
your iPhone? You got your.
No, hang on a minute. No, hold on a minute. I hear that now. I see what's going on. 1 second. I'll mute it if I can't fix it. Thank you for letting me know. Okay.
I still hear it.
All right, so just a minute, guys. I'm just working out what's going on here. I don't know why it's doing that. I'm trying to get it to do its thing. We're almost to a better spot here. Just a second. Okay, here we go. I'm gonna shut this down. This is annoying. Okay, we'll go without. So now, what we'll do is head to another object that I'd like to show you. And to do that, here we go. All right. Here we go. It's hard to read the screen. My apologies. I'm trying to figure out what I'm looking at here. There we go. Okay. So now what I'll do is I'm going to come back and get us off to where I want to take you next. This is actually spectacular. And the telescope will move. See all the streaks? That's the telescope moving. And we can bring that back so you can actually see the telescope. All right. Let's go look at, well, actually I need to come down here and go back into our, this is messing with my head because it's all wrong. All right, so now we have a full moon out, but I think that we're going to try to take an exposure here to see if I'm seeing what I expect to see. All right, we'll do this as 12 seconds. And let's see what we get. A little bright. Yeah. And that's the old one. We're gonna get rid of it. Clear this and go into a new stack here. You know, astronomy takes some time, right? You know, it's pretty cool. Yeah. And let's see here. Well, that's nice to say. And there it is. That's not. That's actually something very different that you've probably never seen before. It is a star cluster. This is called a globular star cluster. And we'll move it over and bring it into the middle of the field for you. All right. Now, this is an object that is, it has a name. It's called the Great Star Cluster in Hercules, or Messier 13. It's famous, world famous. And we have Starlink out at the observatory, and if there's delays, we're waiting for the Starlink satellites because we don't always get them to come in. So you have to just wait a couple seconds for this to work. We generally have very good throughput. But these objects that you see here, these are known as halo objects. These are actually orbiting the galaxy. And they have anywhere between 50,000 to 1 million or more stars in them. And they're very, very old stars. We don't even, it's amazing. Let me do one thing here. I'm going to restart this because I want to make sure that let's do that. No, still doing that. Okay. Whoa, that's scary. That's scary. All right. All right. All right, 1 second. I'm going to try to get back to what we had. We'll do it this way. Okay. Well, I wish I could read that screen. I'm guessing what the screen says. I'm just used to seeing the screen. All right, so we're gonna do this. We're gonna bring this down, and we're going to turn on the live stack here. The live stack is gonna give us image after image after image. All right, so here we go. And you'll see it again. Now, these globular clusters, they number in the hundreds in our galaxy. And they have amongst them the oldest stars in the universe. Okay? Oh, sure, now it's over there. All right, but here we go. Okay, and I'll color correct to make it look like it's supposed to look. All right, and let me see if I can head east and get it to do what it has to do. Oh, it can't because I'm stacking. So let me clear it so we don't have that mess. Yeah, actually, this is actually the guider that we're seeing right here. The telescope has actually two telescopes, one on top of the other, and the other one is a smaller one that's a guide scope. And this telescope, that's a smaller one, is keeping everything in exactly where in the right place. Now, it was moving when we did this, so I had to. It was in the middle of an exposure when I did this, so I have to let it go again. This next one should be perfect. But these star clusters are amazing. The largest one in our sky is one called Omega Centauri. And from the observatory, it's 6 degrees above the horizon, just below visibility for our telescope. It's too close to the horizon. Well, one of the reasons I built that telescope there was I wanted to see Omega Centauri, the biggest globular cluster. It would actually, it's bigger than the full moon in the sky. And you don't even know it's there unless you look. It's really cool. So that said, This globular cluster, Mesha 13, is very well known. It's a cluster that is a amazing object. Hundreds of thousands of stars in this particular one. And the interesting thing about these stars is that every star in this cluster, you might say, hey, there might be planets around some of those stars, huh? You might think that. But guess what? The answer is there probably isn't. Why is that?
Whoa, there we go.
Well, that's why. To those in the stream, one moment, we have a casualty. The screen has blown over. And sandbag.
Let's put the sandbags both in the front.
Yeah. There we go. There we go. I think we're good, yes?
Not the screen. The screen needs to rotate.
One moment,
Put your
folks.
side back just a tiny bit.
If I can.
Yeah, that's better.
Well, we're kind of on a little tilt, so just like stand like this. Thank you, Ben. All right, folks. Ben Hansen was kind enough to help us. It's his screen. There we go.
So if you guys feel a big breeze, yell it out. We'll jump on it.
Now it's going to come from behind, Ben. Thank you. All right, so what I was getting at was I mentioned that these stars that we see in the globular cluster here, these stars are actually amongst the oldest stars in the universe. And the universe is 13.8 billion years old. And these stars might be just about that age. Oh, I'm standing. You know why? You know why. Yeah, to grab it. Well, there's sandbags on the front here. Well, there isn't, but you know what? The sandbags on the front can help actually stabilize too. It can help hold it down. So what happens is these stars are old, and they were formed around the time the universe formed. Interestingly. So what's that mean? It means that in the beginning, the universe had only hydrogen and some helium, effectively. So that the content of these stars is mostly this pure hydrogen and helium. Now, you're made of star stuff, right? The fuel that stars fuse into other elements, heavier elements in stars, right? The way that happens is that they make the elements in the periodic table. That's why you're here. Every element in your body was manufactured in the core of a star at millions and millions of degrees. Kind of weird, isn't it? But it's true. Okay? So that means to me that when you look at a star like the ones here, you're looking at stars that only have hydrogen being fused into helium. And that means that they don't have any of those heavier elements in them. That means there's no elements out there that when those stars die can go into making planets. And that's what we're looking for, is stars being made, making these elements that go into planets. Question back there. What it means is when these, that's a very good question. We actually don't, right now, we don't see many stars that have died in globular clusters. That's because they haven't reached their lifetime yet. Our sun will go about 10 billion years. But these guys are of the right mass that they can go a little bit longer. And we haven't seen any of them die. When they do die, what they're going to do is they're going to swell into red giants, okay, because of a process where they run out of nuclear fuel. Oh, it's just all blue laser, okay? And then, after they run out of their nuclear fuel, what's going to happen is they're going to end up swelling into these red giants and then shrinking into white dwarfs ultimately. And during that time, they may slough off or puff off some of their outer layers, and those outer layers are going to end up being gas like hydrogen and some helium that are going to be pumped off. And that's about it. And yes, those could be made into new stars at some point potentially. You know, it's a very interesting possibility, and that's something that I think we have to keep in mind, right? So these globular clusters are the coolest things in sliced bread, let me tell you. But they're also old, and they're also not very productive in terms of making any planets. They won't make planets, you know. So, okay, the question is, how do they cluster together? I think that's what you said, right? Yeah. Yeah, well, gravitationally, they're held together by their gravity, yes. But the bigger question is, okay, if that's the case, how did it happen in the first place?
Big Bang.
Right? Well, after the Big Bang, we noticed something really strange. The James Webb Space Telescope has really been screwing with our heads. Okay, the reason is because when we look at how stars form right after the Big Bang, we know that stars formed after the Big Bang. We knew that galaxies started to form right after the Big Bang. What we didn't know and didn't expect was that fully formed galaxies could exist only 200 to 300,000 years after the Big Bang. That was an unexpected result, and they still don't have an answer as to why. There is one way that that could be true, and that is if the universe is really a lot older than we thought. Right? Who knows the answer? Well, how big is the universe? What's the diameter of the universe? Now, it's not infinite, because if the Big Bang started, it means it's expanded out to a certain distance, right?
17.3.
Well, we know that the universe is 13.8 billion years old, right? Yeah. But does anybody actually know the diameter of the universe? Okay, here's what happened. When the universe was formed, the Big Bang occurred, the expansion occurred, and it turns out that the expansion is actually accelerating, meaning it's going faster and faster every second as it expands. That's an unexpected result. We did not expect that. What that means is that the universe could possibly be younger than we thought. But wait, didn't I just say it could be a lot older than we thought because we saw fully formed galaxies? And the answer is yes. So you can see where cosmology is now sitting at a crossroads saying, I don't know what part of this to believe. I have no idea what's really going on, they'll tell you. All we know is we need more data. But keep in mind that this expansion has been going out for a certain amount of time. We can see out 13.8 billion years. But how long did it take that light to get here that we're seeing going out that far? It took it 13.8 billion years to get here. And in that time, the universe has expanded even further, right? So when you add it all up and you take into account the acceleration outward, we find that the actual size of the universe in diameter is 92 billion light years in size. So we see out 13.8 billion years, a pittance, and there's so much more beyond that. And this is because of the time machine concept I told you about before. When we look in the sky, everything we see is at a different time in the universe, right? And when we look at the cosmic microwave background, the residual remains of the Big Bang, we see a ghost of the original Big Bang from 13.8 billion years ago. But the universe has been expanding ever since that light got to us for another 13.8 billion years, and it's accelerating out. So that's why the actual size is 92 billion light years in diameter.
So then there's actually something bigger than the universe because the universe is expanding into it.
Okay, we're getting a question that's a really good question. The question is, so the universe is expanding into something. And then my question and your question would probably be the same. What's on the other side of what it's expanding into? Where is at the end, what's next after that, right?
Right.
I don't know. Cosmology doesn't understand that. Astrophysics can't tell you, and astronomy certainly is baffled. All of us have no clue.
So
That's what makes this so exciting.
your telescope can see beyond the furthest star.
Well, you know what you need to do is you need to have a telescope that's really, really big, like the James Webb. It needs to be way, way out in space, and it needs to be able to look at the farthest things we can see. But here's the problem. Our telescopes are limited, and here's how come. The James Webb looks for infrared light, doesn't it? Remember? It's an infrared telescope. What good is that, you might say? Well, Edwin Hubble in 1929 discovered something amazing. He discovered that the farther away galaxies were, the faster they were moving. Oh, again. Okay, we lost the screen again. Thank you for the warning.
I'm coming. Why is Mark breaking my screen?
I'm not trying.
You want to grab that side?
I got it.
It needs to go a little bit to your side. Go.
We'll find something heavier.
Do we have any volunteers who want to lay on the other side?
We need bodies.
Just kidding, folks. Just kidding. Actually, that came back pretty well.
What kind of adjustments would you have to make to look at the moon? Do you have to have a
I
filter
could-
on it?
We could point it at the moon, but the moon's kind of low and it is full, so there's not going to be much detail, but we can do it.
An announcement. Somebody's phone was on the ground.
Oh, okay.
Yeah, it was just on the ground. So perhaps it's still somebody who's here.
Okay, this is a found phone. It has a beach scene on the front with an umbrella in a chair that's in the water. And it's probably someone's pride and joy is on here along with all their photographs. So,
There's a lady looking right over here.
okay, that might.
Oh, the lady, she's the announcer lady with the little dog. You know, the one who says
I
everything-
saw.
Little dog.
Yeah, she says everything's beautiful up on stage. Beautiful, beautiful.
Okay.
She introduced the panel.
Well, we're gonna put this phone right here so that if she comes back, yeah. To those of you listening out there around the world, we actually we just found a lost phone. This is a live event, so this is kind of cool. We lost the screen twice thanks to some bouncing around of the wind, and Ben Hansen has been taking care of it. Ben's a good friend of mine. He's also doing night vision, and he's a Skywatch Pro and a pilot. Almost good one. And yes, he is an amateur astronomer as well.
I've made as many landings as takeoffs. That's all that matters.
I made as many landings as takeoffs, he says. That's very good. So we talked about the size of the universe being 92 billion light years. And that's something, like I said, that cosmologists can't get their head around because with the universe expanding faster than we ever thought and accelerating outward as it goes, that tells us that the universe is actually younger. Because by reverse engineering what Hubble found and then what we see, it means that the universe should be younger. Yet fully formed galaxies means the universe is actually older. And that's something that we can't put together yet. And I love it. Question back there, yes.
Assuming that we are correct that it's accelerating at an increasing rate, will there be a time when we will no longer see stars?
The question was, if we're accelerating at an ever-increasing rate, will there be a time when we won't any longer see stars? The answer is yes, indeed. In fact, that's one way in which it's hypothesized that the universe will die. And that is because eventually everything will be moving away so far from each other, and I was telling you about the speed, I'm going to get back to that in a minute, that all of the light from any of the objects we see will long since have been either dimmed by distance or it'll be further out into the infrared. Now, why is that? Because in 1929, as I mentioned, Edwin P. Hubble discovered that galaxies moving farther away from us, or galaxies farther away from us, are actually accelerating further away faster. They're actually moving faster and faster. What's that do to their light? Well, in sound world, well, light, when the sound goes by you, you hear a train coming, goes, you hear that pitch change, right? Well, light pitch changes as well, but you don't hear it, of course, you see it. When light comes toward you, it's bluer, and as it passes you and goes past you, it gets redder. You can imagine that if something moves much, much faster, farther away, faster and faster and faster, its light is going to be shifted almost entirely into the red end of the spectrum and beyond. And what's beyond the red visible part of the spectrum? The infrared, which is where the James Webb is looking. So the James Webb, pointing at distant galaxies, has seen galaxies that we have never seen before. Galaxies that are moving so fast that all of their data is far, far out into the infrared. That's something that is a finding that was expected, but not to the extent that we discovered. That was incredible. Yes?
Follow-up question. If everything is expanding at an accelerating rate, what does that mean to us and our atoms inside?
Question is, if everything's expanding at an accelerating rate, what does that mean to us and our atoms inside? Absolutely nothing. Because you're a unit that's moving with something else that's expanding, and that is the entire solar system. The sun is moving around the galaxy. Does anybody offhand know how many times our sun has gone around the galaxy since the Earth formed? That's 4.6 billion years that we've been here. It's orbited the galaxy about 20 times in that time. Pretty cool, you know. And so when you talk about that, the whole galaxy is the thing that's moving in some direction. So relative to other stars, they're not just going to wink out like the ones we see here, okay? All the stars you see here, they're not going to go away. They will go away when they die and they run out of their nuclear fuels. But they're not going to die or just wink out before they die. That's not going to happen because we're moving with them. We're all going at the same rate. Question over here, yes.
What is causing them to go away faster? Why are they accelerating? What is the momentum that's causing the acceleration?
So the question is, what's causing the acceleration? I assume you mean of the universe.
Yeah.
Okay, that's interesting. We thought that there was a constant expansion rate, and that became something known as the Hubble constant. Again, Edwin P. Hubble came up with this. It's a certain number of kilometers per hour per megaparsec. It's units are not quite that, but anyway, so that number became an acceleration factor. Well, now we see things are moving faster and faster every second. So what's prompting that? We didn't know. So in order to explain it, we came up with something else, and that something else was called dark energy. That's where dark energy comes from. Dark energy is a repulsive force, and it means it's nasty, right? Well, it means it repels everything around it. And is it real? I don't know. I have my doubts. Yeah. So anyway, I think that that's a very interesting concept, dark energy, and I think that it's something that remains to be seen if it's actually real. Any other questions before we wrap up?
Did the James Webb kind of recently tell us that everything that looks like a star is really a galaxy?
No, the James Webb, the question was, did the James Webb tell us that everything that looks like a star is really a galaxy? No, every star you see over here is within our galaxy. Every star in this image is within our galaxy. That object right there is actually a little further than the stars because it's outside of our galaxy, but it's orbiting our galaxy. It's what's called a halo object that goes around our galaxy, and that's actually what a globular cluster is. All right. So, but the James Webb was showing us galaxies we've never seen before. So, in other words, when you look in the sky, the section of sky, there are so many galaxies up there that we never knew were there, and the James Webb has shown them to us. Now, in astronomy, we have a problem called missing mass. There's not enough mass to have created the Big Bang. So we started making up ideas that maybe we're a parallel universe. Maybe there was other explosions, other Big Bangs. Maybe we're a mini bang and there's a macro bang, and all these things might have happened. And so we wondered about that. But it turns out that it's possible that we just didn't see all the rest of the mass, and maybe telescopes like the James Webb are going to show us all the rest of that mass. See? The question is, does it have anything to do with antimatter? I'm repeating your question because we're broadcasting, so yeah. Does that have anything to do with antimatter? No, not really. Antimatter does exist. Okay, there's antiparticles for regular particles, but this is not an antimatter question. This is just a question of mass in general. Okay, not anti-mass or anything like that. Just mass in general. So, question, yes? Yeah, dark energy is an interesting one. I just mentioned it. Dark matter is a substance that we see that keeps galaxies rotating in a cohesive disk. Thank you. Good night. All right. And that cohesive disk is very interesting because galaxies, like we saw before, should have wound up, right? Their spiral arms should have wound up long ago. But they didn't. They haven't. And the reason is because there's a mass of some kind that's helping those outer arms to spin at almost the same rate as the inner arms. Okay, you'd expect that they would have wound up because look at Mercury. Mercury zooms around the sun every 88 days. Pluto takes well over 250 years to go around the sun. So the farther away you are from a center of gravity or a center of a galaxy, the slower you should orbit. So we'd expect those arms way in the outside to kind of lag way behind and wrap around the galaxy multiple times. But in fact, it's not what we see. So that's where the concept of dark matter came from. Okay, and the dark energy, on the other hand, that's what's being used to explain the acceleration of the universe. As things move away from us, the further they are, they're actually accelerating outward, not just making a constant speed. So that's the thing that I find really interesting. Anything else? Oh, really good question. We do have a galaxy coming toward us. I wish I could show it to you right now, but it's not up right now. It's called the Andromeda Galaxy. It's 2 million light years away. The one we saw earlier was 20. The Andromeda Galaxy was 2 million light years away. It's the size of your thumb to your pinky, stretched like this, in the sky right now. That's how many degrees it takes up. Okay, but it's going to be here. You better pack your bags because it's going to be here in about 2 or 3 billion years. And it's going to collide with our galaxy. It will probably tear us apart. It's got about 1 trillion stars in it to our as high as 400 billion. Okay, so it has easily double or more the stars we have. So it's got a mass that's much larger. So it's probably going to tear us apart. Is that going to spell the end? No. We'll just keep going along. We'll just change the way in which we survive and exist. We'll probably get an influx of all new gas and dust from the Andromeda Galaxy. And the next thing you know, we're going to have an amazing new galaxy with maybe all kinds of new star formation. It's going to become a very busy place. Well, I hope you guys had a good time. All right, and I apologize for the screen, but you know what? It's the best we can do.
Oh my gosh, thank you.
Thank you guys. I'm glad you came. And when there isn't a full moon, I'm sure we can spend a little bit more time. If you want, I can give a shot at trying to look at the moon last.
Why not?
Why not? It's full. You're not going to see much, but we'll try it. Yes, that's right. Man on the moon. That's better than Man of La Mancha. All right, so let's see here. All right, good. So we're going to come over here, and we're going to get rid of this stack here. That looks like the one. And we're going to go back to a 1 second exposure here. Okay. And then we're going to go into our night vision mode here. So there we go. All right. So let's go see what it's going to take to view the moon right now. This is interesting because the moon is very bright. And I'm certain, as we zoom out, I'm certain that we'll be able to check out the moon. If it's high enough in the sky. We got to make sure it's high enough in the sky. And that's the most important part. Oh, well, actually, We'll give it a shot. We'll give it a shot. It may not be high enough in the sky. And when I say that, it means that we have the walls of the observatory. And we'd want to make sure that the walls of the observatory aren't blocking us. But we're going to try it. There we go. We're zooming. Oh, and we'll know right away whether we can see it, because it's going to fill the screen and be really, really bright. Well, there it is. Yeah. I have to bring our exposure way down to just a few milliseconds. I think I'm going to have to go down to like 25 milliseconds maybe. Let's try it. All right, maybe a little more. All right, let me just drop that down a little bit more now. We're going to say 10 milliseconds. And we're going to go even more. Let's drop it down. Drop it down. All right, well there we go. That's the moon. Yeah.
How about the zoom? Is this maximum zoom?
No, this is the native size of our chip. Okay, we're actually viewing this moon at just about the size of our chip. It's actually still, it's zoomed a little bit. I can zoom on this. So give me a.
I'd like to see more detail.
Yeah. Let me show you though the size of our sensor. This is the full size of our sensor. Okay. What you're seeing here, all right, is this is 2 degrees across and 1.5 degrees tall. You can see if you put these up, you'd have 4 full moons that go across here, and 3 full moons that go. Oh, sorry. You'd have 4 full moons that go across here and 3 that go up and down. So it's a 2 degree by 1.5 degree field. That's the size of the field, because what we do is we generally do a lot of Milky Way surveys with our telescope here, this particular one, and then we actually capture vast tracts of nebula that go many degrees in the sky, right? So if we now go and like zoom in on this, the sky out in Arizona is a lot clearer than it is here, but let me try to zoom.
Have you ever spent long enough time to notice something unusual, like objects flying in and out?
We've actually seen, for instance, we've seen objects that have crossed in front of the moon. Okay, and usually those are satellites in our Earth orbit that are crossing in front of the moon. Yeah, that's right. We actually let me come here. It was January 20th of 2019, and we're streaming live. And thank you for reminding me of that, Marianne. And what we found was we saw this bright flash hit the moon at the height of a lunar eclipse. In the red area, the dark red area of the moon, there was a flash. That flash was a meteor striking the moon. And we captured it, and it's up on our website. You can see it on our YouTube channel, SkyTour Livestream with Mark D'Antonio, and we can actually tell and see that this meteor hit, and it turns out we were one of 5 groups on the entire planet that saw it. So that was pretty cool. So that's our claim to fame, if you will, I guess. I don't know, but it's neat. Let me zoom a little.
Yes. Do you have that phone you found?
Oh yeah.
Can you describe it?
That's not it.
That's not it?
That's not yours?
There's another one up there at that desk, I'm told.
Which desk?
The check-in desk. Go look
Way
at
up?
that. No, right
Hi.
there where they're meeting.
Right on, that's where it is. Thank you guys, sorry. I'm glad I'm not the only one that lost one, and excuse me for interrupting.
Oh, that's okay. Phones are a lifeline now.
Standing there holding the post.
Okay, so here's the problem with the full moon. You don't see shadows. So it's hard to see the moon as focused when it's a full moon, because you don't see any of the shadows. Only near the extreme edges would you see shadows. And unfortunately, it's so washed out that even with a great telescope like we have, you're just not going to get the same kind of detail that you might normally get, right? So I think Ben's trying to refocus now, just to squeak a little extra out, but it's only going to get to a certain point. But what you might see, even like this, you might see a black dot slowly traverse across the moon, and that'll be a satellite possibly traveling in front of the moon. And there it is. That's a camel. There's a camel. He couldn't resist that, I know. Great. Well, anyway, there you go. So there's your moon for tonight. I'm mooning you. I'm giving you the moon. So I hope you guys enjoyed it, and you guys have a good night, and thank you so much for coming. Oh, you're more than welcome. And to those of you on the stream, we're going to be cutting it off now and heading on out. I want to let you know that I appreciate you being here, and we will come back. Thank you. Thank you very much, guys. Thank you so much.
Would you like me to bring the lights up right away, or you need some time?
Oh, no, we'll be fine right now.
Go ahead and bring them up?
No, I don't need them right now.
Okay.
Yeah, we'll be fine.
About how long?
Well, if they need to, for safety, if you need the lights up, you can bring them up.
Well, all the people leaving, yeah.
Yeah, all right, I want
we
you
prefer
you can bring it up then.
Okay.
I'm not going to argue with you. That's a good point. All right, folks, so what I'm going to do now is I'm going to close everything down. You can ask anything. Yeah, what about it? Yeah, it's a great satellite.
Photograph the lunar lander and all the trash that's on the moon, and show the shadows of the flag and the lander.
Well, that wasn't Clementine that did that. A lunar reconnaissance orbiter has done that. And the LRO Quick Map is something you can get to online, and you can see the moon in extremely high detail, right down to 5 meters per pixel. And you'll have a great time. You can see the tracks, you can see the rovers, you can see the base of the lunar landers that have landed there. I even found the remnants of the crashed lunar modules after they went back to the command module in orbit and they dumped it, and it crashed on the moon. I actually found the crash streaks along the moon where that actually happened. So amazing stuff. Amazing stuff. And the question was, are there images of the backside? The LRO, Lunar Reconnaissance Orbiter, did in fact...
did you warn the night vision goggle people?
Okay, hold on, guys.
Are you doing this again tomorrow?
No, this was the only night for the... for this. Well, you're welcome. Thank you for coming. I know this is a little crazy, guys. Give me a few minutes.
In the background, some thought to be artifacts on the negatives, but when the Asian country launched their own, that government, who's usually kind of communist, they just released the images of their digital camera technology.
You talking about China?
Digital camera technology, thousands of times better, and they don't have the right aperture, right iris. So their digital cameras were able to capture similar iron raindrop background, and it's released on the internet, correct, according to Hoagland.
Okay.
So did they determine what that was, or what Hoagland is suspecting is their glass structures?
I don't know, but Richard Hoagland doesn't have the scientific background to really make any kind of judgment of it.
Correct. So announcing it, are the scientific community backing it up?
I actually don't know if they are. I have to look. I don't know. But that's pretty clever. It'd be pretty cool if it was true. Yeah. I do know that there's the Aitken Basin on the other side of the moon has a potentially large impactor under the surface from when an asteroid struck that was high iron content, and that would be a very interesting thing to check out. Yeah. I have another question.
Any corroboration with Mike Barra, same artifacts?
I know Mike Barra. I don't believe a thing he says. I'm kidding though. He's a good friend. Yeah.
So here's kind of a far-fetched question that I've heard tossed around a few times.
Okay.
That is that people said that there's a speculation that the moon could have been placed there.
The question was, could the moon have been placed there. We have the moon up on the screen, as you can see, guys, in the audience. The question is, could the moon have been placed there? We find that there's no reason for the moon to have been placed there. And the reason is because when we look at the moon, we can see that the moon is made of the same type of materials as the Earth. Okay, it's nothing drastically different at all. The only differences have to do with the way the surface of the moon, without an atmosphere, have been affected by radiation from the sun over billions of years. That does transform things a little bit, but there was speculation, well, the moon is hollow, the moon rings like a bell, that's how we know it. Well, a bell, if you know what a bell looks like, a bell actually has an opening at one end. Well, the moon doesn't have an opening at any end. So when you have an object that rings like a bell, that's a planet, it doesn't mean it's hollow. Actually, a hollow thing would go bunk, all right? But it's a solid thing that would go bing, okay? And so when it rang like a bell, there was a seismic experiment that kept detecting waves going back and forth. What those waves were doing was they were going through the center of the moon, going to the other side, to the underside of that outer surface, and bouncing off and bouncing back and forth. The conduction of the sound was so complete that it rang like a bell. And that doesn't say the moon was hollow, it says exactly the opposite. It's actually solid and actually fairly uniform. There's a park in Pennsylvania called Ringing Rock State Park. And when you go there, they give you a hammer and say, bang our rocks. And when you do it, they go bing, and they ring. The reason they do that is because they're solid. And they're made of a homogeneous material, almost the same material throughout. So that ring is rather complete. It's amazing. So you go bing, and they just ring, ring, ring. And it's because of the solidity of the rock, not because it's hollow. See? And so the moon being an artificial object, I never bought it. There's no reason for it. And people say, well, look at the moon. The moon is like the only moon of its size relative to the planet Earth. True. I mean, we do have a fairly large moon relative to the size of our planet. Okay? But why? Well, if you think about how it happened, the moon was formed by a potential collision with a Mars-sized object. And that collision could have sparked the moon, could have chunked off the moon. At a time when the Earth was young, when the moon was created, a lot of material was thrown off the Earth and made a ring around the Earth, kind of like Saturn for some period of time. Much of that congealed into the moon. It was far enough away that it could stay there and stay unified and and be a fully formed body and not be broken apart by tidal forces because of being too close, And so that really is the genesis of the moon, in a sense.
An excellent explanation and clarification.
Yeah, well, that's something.
That theory's been thrown around a few times, and it sounds like you've covered it quite well.
Well, thank you. I mean, it is something that I've spent a long time working on, obviously, Yeah.
Mark, so I've always wondered, so when you guys have mapped our galaxy and then other galaxies, is there enough distance between them? That's how you're able to determine and it has all that been mapped from telescopes on the Earth, or has that been aided by photography or whatever from space oriented?
Okay, so the question is, how did we have the ability to map the universe?
Right. Well, like our galaxy, you can show a 3D model of our galaxy, and I'm going, well, we haven't sent anything out to the edges of our galaxy, so how do you guys essentially determine the extent of our galaxy and where another one starts?
Okay. Well, we have something called the cosmological distance ladder. It's a way to determine distances, and we can determine distances to galaxies like the one we saw before, Messier 101, that spiral galaxy. And we can determine distances to stars too. And this cosmological distance ladder, there's a number of ways in which we can determine distance, from parallax all the way to variability of certain stars that that do the same thing over and over that we know. And that's how we can actually find galaxies. Those are called Cepheid variables. And he's nodding because he knows, okay, behind you. So, but these variables, okay, and the parallax question, I actually did parallax studies in an observatory, and in fact I took parallax imagery to determine the distances to nearby stars. And this whole process only works out to a certain amount for parallax at a certain distance, okay, maybe 300 light years or so. Beyond that, you need another cosmological distance candle, and beyond that another one and another one, and we have those. You know, we have what are called type 1a supernovas. Those also can tell us how far away a galaxy is, all right, or how far away the supernova is if it occurs in our galaxy. So there's a lot of things that we use as a distance ladder to tell us how far away things are, you know. And as far as stars themselves, we can tell that stars move, and what we can do is we can do these minute measurements, and we measure what's called the proper motion of a star. And that proper motion allows us to be able to determine the distance of that star, how fast it's moving, and where it's going. Then we can have the orbit of the star. We can say, oh, this star is going this way around our galaxy. It's going to go around the galaxy right here. We can even calculate if we'll ever have a star that's going to pass close enough to us to be a danger to us and go supernova, for instance. We don't have any stars like that now, and we're not going to in the foreseeable future. But we can calculate now, because we've measured these distances and the movements of these stars, to actually calculate how their paths are going to move throughout time. Think about the complexity. Each star has its own gravity, and you have to calculate the effect on this star from this other star over here, another star over here, another star over here, and those are all moving.
Right, right.
So you see it gets complex very fast, and it's called an N-body problem. N is in November. N-body problem. And solving N-body problems has been one of the biggest conundrums, the biggest things we've ever had to do in astronomy, cosmology, astrophysics. And it's something that doesn't get easier with time. We still have to do it all computationally with a computer that's very high-end, you know, or computers, or a bank of computers, or years of research, you know. But we do have the cosmological distance ladder to tell us these graded distances to different objects.
It's hard to get my mind around when you know, do a tour where your perspective is from outside our galaxy, looking at that, and then traveling through space at all these other galaxies. It's just mind-boggling that we can figure all that out, because there's millions of measurements, like you say.
It is mind-boggling to try and figure it all out. You're absolutely right. Right? But we do it, and it's done by supercomputers now as well. Computers that would make my fast computer look like a baby, you know. And then in the end we can just say, well, let's just look at the moon, because we know that's easy. Right? Well, of course we like looking at other things, but I hope you guys enjoy this, because I never get enough. So I'll probably keep talking till the chairs are empty and folded up and gone, you know. Yeah.
First galaxy, did it have a name?
Yes, that was called Messier 101.
The very first one before that.
Oh, look at that little guy. Oh, is that?
The last one? No. Yeah, nope, not ours.
Oh, okay, sorry.
Thank you.
No, it's all right. Please ask again.
Was that the very first one you showed?
Yes, the first I only showed one galaxy tonight.
Oh, okay.
Yeah, and that was Messier 101. Now, why was it? What's the 101 mean? The 101. Sorry, this is a throat spray. It's for people who sing. I don't sing, but it helps my vocal cords, because it may not be obvious, but I was actually blind and quadriplegic 8 years ago. So I've kind of done a little work to get better. So I have a paralyzed vocal cord, so I have to spray every now and then. So the galaxy that you saw was called Messier 101 because Charles Messier in the 1700s was building a list of very cool objects. But for him, he was a comet hunter. So he was looking for smudges of light in the night sky with his telescope and saying, oh, that's not a comet. I'll just call it Messier 2 and move on. Oh, that's not a comet. Messier 3, move on. And then he made this catalog of just over 100 objects that became a famous catalog of the cool objects in the sky. And we call it the Messier catalog. And it's the coolest thing in the world. You know, and the people have Messier marathons where they see every single object in one night. I have been asked to do that with this, and with this telescope I can't do that because, well, it's not that I don't want to. It's partially because I don't want to. Okay, it's a lot of work. But it's usually because the telescope has walls that will preclude us from looking low to the horizon when needed. And that's okay, because stuff low to the horizon is in smudgy sky. The air is turbulent, and it doesn't look very good. But you have it as your Messier object, right? So that's why. But we can't do that right now with this particular telescope. The next one, we'll be able to do that, because I've developed a new building that's going to allow the next telescope, which we're going to get in a couple months, to actually be able to see all the way around. Yeah. That is such a good question. The question was, guys, talking to them, the question was, why doesn't the moon spin around? Why do we always see the same side? Okay. Well, the answer is the moon is spinning around, but it only goes around once per revolution around the Earth. Watch my hand. I'm the moon. I'm going around the Earth right here. What am I doing? The same face is facing the Earth, right? Right. But if you look at that from the top, the moon's doing this. Right? If you look at just the moon, it's going to rotate one time for every revolution around the Earth, right?
Isn't that unusual? Like, why doesn't it spin more?
Well, because that's a process that happens because the moon is close enough to the Earth that the Earth's gravity can affect it differentially, meaning that the Earth's gravity on the near side of the moon is going to pull it in such a way that it kind of holds it from rotating. And it's not unusual. Jupiter's moons, all right, yeah, Jupiter's moons are tidally locked. That's what this is called, tidal locking. Mercury is partially tidally locked to the sun, okay? Other moons around other planets in our solar system are tidally locked as well. It's very common for moons around planets to be tidally locked, especially if they're close. Gravitationally means that the gravitational force from a planet is tugging on a moon. But if the moon is in orbit and it's close to that planet enough, then the gravitational force on the near side of that moon is more than on the far side. So it tends to keep it aligned. Okay? And effectively that's tidal locking. And then we see that with a lot of moons in the solar system. Yeah, right there.
Do you know anything? Would you be able to talk about like gravitation?
I don't know anything. No, I'm just kidding. The question was, do I know anything? But not, he didn't finish his sentence. Do I know anything about what?
Gravitational waves.
Absolutely. Gravitational waves are the coolest thing since sliced bread. Einstein said we probably wouldn't ever detect them, but we did. And that's very important. Now, you didn't see my lecture on UFO propulsion today, or that was yesterday, I think. Yeah. The days run together. But UFO propulsion is very interesting because if you look at the way fundamental forces work in quantum mechanics, we have the weak force, we have the strong force, we have the electromagnetic force, light, and then we have gravitation. Well, every one of these others, you know, the weak force, the strong force, and electromagnetic force, we know how those operate. We have equations to describe them, and we can describe them as waves or as particles, right? They can be you can actually define them those ways. Gravity's different. In gravity, we wanted to find whether it had waves or particles. The particles of gravity are called gravitons. I talk all about these in my lecture.
Give me a heads up, I'm talking with the place. They're about to shut the lights back off.
Okay. Then Ben wanted them off.
Yes.
Okay.
Yeah, they were supposed to come off.
Okay. That's okay. So, when I talked about, in the lecture, I talked about gravitons, but you see, if we think about the way an alien civilization would maneuver and get here from such vast distances, they can't do it if they just go place to place. If they're going from, say, Alpha Centauri to here, at the fastest possible speed they can go, just under light speed, it's still going to take them more than 4 or 5 years to get here. Okay? Because they can't go light speed. Right? Light speed is not going to work for corporeal beings like us. You can't do it. Okay? So what do? Well, it's 4 dimensions, X, Y, and Z moving through time. That's us. Let's call that our membrane, our universe, right? Now go into string theory, and in fact, a variant of string theory, if proven correct, I think is going to really come out to be the way they actually move and the way they get here. What they do is they actually can leave our 4 dimensions and go into a 5th dimension, all right? And that 5th dimension has a name. It's called the bulk, B-U-L-K, right? And the bulk is a highly warped dimension, all right, next to ours, so think of it that way. And it's so warped that the more you go into it, the closer everything in the universe is to you. The universe is shrunk around you at that point, okay? And when you shrink the universe around you, now it means that with a shrunken universe, you can now go places in that shrunken universe much faster. So Alpha Centauri, one of the calculations done is that Alpha Centauri, 4 light years away from us, would take us at the fastest possible speed we can go. It would take us about 12,000 years to get there. Okay? However, if we actually were to use this theory and go there using these special particles that we can generate with as little as a fusion reactor, we can get there in 20 minutes. Because we punch out of our 4 dimensions, go into the bulk, and punch back in near Alpha Centauri.
You would do that using gravitational waves?
Well, gravitational waves would actually probably be a counterpart to this. But I'm talking about a methodology by which UFOs would travel. And what they do is they create these special gravitons that are 10 to the 16th times more powerful than our own. Now, you know, you're thinking, oh, here we go, we're going to science fiction. Actually, we're not. If you want to learn about it, you go to the CERN website, CERN, you know, overseas. CERN is investigating these very particles, and their particles are called Kaluza-Klein particles, K-A-L-U-Z-A, Klein, Kaluza-Klein particles. And the Kaluza-Klein graviton is 10 to the 16th times more powerful than our gravitons that are holding you down right now. So, in fact, and this was the topic of my lecture, in fact, a UFO is generating an extremely high gravitational field. And when it creates these tiny Kaluza-Klein gravitons and surrounds its ship with them, what an offshoot of that is it's creating all these micro black holes as well. Now, micro black holes sounds all dangerous and everything, but they only live a few nanoseconds, and then they evaporate. But in that time, they're pulling in a little bit of light, maybe a couple of molecules, whatever, of atmosphere. And to your eye, a ship using a sheath of these Kaluza-Klein gravitons will appear to shimmer. It'll appear to change color. It might wink out of existence in one place and appear over in another. Okay? So that process of the Kaluza-Klein process, the Kaluza-Klein gravitons, is something that would actually be very fruitful to an alien species, okay? And if you think about it, every observed report that we get about UFOs, you also hear, well, it shimmered in the sky, it disappeared here and it reappeared over there, it was changing colors. You can't deny that that's potential evidence of Kaluza-Klein gravitons in play, right? Because it matches what we would see. Now, I'm an astronomer. I can tell you that something shimmering and changing color, well, that could be something we call atmospheric scintillation. A point object like a star close to the horizon will be disrupted by the air and it will dance around and will change colors. Okay, so yes, that'll happen. Something disappearing in one spot and reappearing in another, yes, that can happen too. We call that the autokinetic effect. Your eye, looking in this blank sky, might see something, but if it winks out of existence, and then winks into existence, your eye is doing this. It's dancing around all over the sky trying to find it. And then when you see it again, you'll think it's in a different place, but in fact it's just possibly going in a straight line. I actually did that experiment. I was teaching a boot camp, and I was running my camera quietly in the background while people were watching this object dancing around in the sky. And they said, now it's here, now it's there. It's dancing all over the sky. They were shining lasers at it saying, it's listening to us. And then I showed them the photo I took, and all you saw was a dash of light and then nothing. Then a dash of light and then nothing. Dash of light and nothing. Do you know what that is? It's a tumbling rocket body. When it was end on, you didn't see it, but when it went like this, you saw it for a little while, then it went gone again. Every few seconds, it would do that. A tumbling rocket body. And we call them tumblers. Go figure. So these tumblers can really fool your eye and make you think that you're seeing something that is not in the same place over and over, but in fact it is. You know, and there were people there who watched it happen, watched me take the picture, and still didn't believe that it was the same object. You know. Any other questions? Oh yeah, you had a follow on. I'm sorry. We were talking about the globular cluster, the stars in the globular cluster. She was asking Gang about a object that I might have said had appeared when the universe was born. Well, a couple things I said. I said that we found with the James Webb Telescope that there were some galaxies that were fully formed that should not have been fully formed if our theories and understanding were correct about the universe. And so that's something that is a conundrum that we don't know the answer about yet. And we do know that it probably has to do with the fact that our knowledge of galaxies early in their existence is not complete, for sure. So I said that for sure. But then I was showing the Messier 13 globular cluster, and the Messier 13 globular cluster has stars in it that are about as old as the universe is. And those stars, being very old, would be stars that are very low in any other element but hydrogen and helium. So we wouldn't expect there to be any planets around those. All right? So there wouldn't be planets there. There couldn't be. Because there would be no materials with which to make planets, like magnesium and iron and nickel and potassium and so forth. That kind of material would not have been made in those stars. You follow?
I think so. I think I'll have to go back to those again.
Okay. Yeah.
How long do you think it will take before the new telescope Webb is able to detect another solar system, or within our galaxy, or another planet in another galaxy that has Earth-like atmosphere?
The question was, how long we think it'll be before the Webb could detect another planet in our galaxy or another galaxy, and detect an atmosphere like our Earth's, either in this galaxy or another. Okay, looking at another galaxy presents additional problems of distance, of course. But looking for instance, if we look at the Webb now, the Webb Space Telescope can indeed, and has, found new planets already around other stars. It's found, we call it exoplanets, right? An extrasolar planet is the same. Okay, in astronomy, I've focused on exoplanets. My book, The Populated Universe, talks all about exoplanets and how they relate to our planet here and how they were formed, etc. So, but the time it might take, when we might be able to discover this, that's a good question. I can't tell you because we're still unfolding all the Webb discoveries as we go, and there's plenty of them, But as far as another galaxy, that presents problems because, first of all, we need a telescope that can discern separate stars in another galaxy. And the Webb can do that to some extent, but the galaxy has to be near us, you know. And as the galaxies are moving far away from us, in fact, here's the way the universe is expanding. Here's a way to think about this that you'll be able to think about. Take a balloon, blow it up to about the size of a baseball, and put little black dots on it everywhere, okay, with a Sharpie. Then continue to blow it up. As you do, you'll see that every black spot is moving away from every other black spot in all directions, no exceptions. That's a metaphor for how the universe is expanding. And as you do that, blow harder into the balloon and make it expand at an accelerating rate. And that's what we're actually seeing. All right? So...
But aren't at the same time new stars created? New
and the same stuff, and yes, and the question is...
So they fill some spaces up.
But except that that's happening within galaxies. So the question is, at the same time stars are being created. Yes, but it's happening within galaxies that are also being created when the universe was created.
Okay, then galaxies are getting apart from other galaxies. Things within the galaxy stay the same. It's only the galaxies that are becoming more part of one another.
Yes, exactly right. We know that that's true. The only way, but there's a little wrinkle there, and the wrinkle, he was saying that the galaxies would only be moving apart from each other, and that within the galaxies they'd stay the same. That's correct. But if you look at galaxies in general, like ours, we have companions. We have two smaller galaxies that orbit us. They're called the Magellanic Clouds, but those are actually small dwarf galaxies. And then there is another dwarf galaxy that was found more recently that is also around us. And then we have what's called the local group, 30 plus additional galaxies within our galactic neighborhood. And those more or less are all moving together through the universe. We're actually moving, where did it go? We're actually moving toward the star that's over there.
Smaller galaxies group and move together.
That's correct. Smaller groups of galaxies will move together. And Andromeda galaxy is pretty large. But that galaxy is in fact moving with us and several other galaxies, 30 plus other galaxies. And that's called our local group.
Clusters.
Well, yeah, and we are, you might call us a small galaxy cluster, yeah. And we're actually heading toward the most massive galaxy cluster we know of. And it's in the direction of the constellation Virgo.
Anything about Nibiru?
Nibiru is a object that was rumored to exist. I don't believe in it because we see no evidence for it. We don't see any evidence that Nibiru occurred.
I watched a NASA presentation. They proved the existence of it through observing how the light wave changes. So they didn't see the physical planet, but they observed how the light changes when the planet goes over the horizon. And this is how they determined there's something huge, a big mass with two moons, like two dwarf planets around it. I watched that on. It was on NASA.
Yeah, we have our solar system's a really dirty place. Okay, we actually have a belt of icy objects that are, dirt mixed with ice is far, far out beyond where Pluto is. That's called the Kuiper Belt. Yes, that's right. You got it. Okay, and the Kuiper Belt is also joined by the Oort Belt, which is a little farther out, and then there's an Oort cloud. That is a cloud of cometary objects that are in a spherical halo around our solar system. And it turns out that spherical halo around our solar system extends out almost half the distance to Alpha Centauri. So it goes out several light years from us. So we didn't know that. Obviously, we've been seeing that that's the case. So anytime you have something at a great distance that passes by, like a star, it could perturb or disturb, that's what it means, an object to end up moving toward our inner solar system. And maybe this is where some comets come from. The Oort cloud has been thought to be where comets come from, right? And so that may be true, We'll have to wait and see. But I'm not going to be around for that. You know, 'cause that'll be several hundreds of millions of years to become noticeable to us. So we good? What do you think? Was it?
You have to go. You're tired.
I'm all right.
Avi Loeb was talking about the anomaly because usually comets are going to be round and then they can tumble and spin.
Yeah.
You got it.
The comment was Avi Loeb was saying that objects that are comets are usually round and possibly can tumble and spin. Is that what you're saying? Well, actually, the reason that things tumble, especially comets, is because they have gas. I see you back there. I'll get to you in a sec. The reason comets couldn't actually tumble is because they are filled with all kinds of ices and so forth, and when the sun starts to heat them up, they start to eject some of the gas that's caught in pockets in the ices, and that acts like little jets, and that'll start to maneuver the comet. And like, for instance, Comet Churyumov-Gerasimenko, 67P, the Rosetta mission comet, where the Rosetta mission went to, had jets, massive jets coming out from it the entire time that the Rosetta mission was there. So you could see these, and it's incredible. And that's exactly the kind of thing that causes comets to take up weird emotions, you know. Yes, in the back you asked a question. Oh, okay, never mind. So yeah, now I know Avi actually. I talked to him somewhat recently, and then I talked to his Galileo team because Jacques Vallée actually introduced me to Avi because Jacques and I know each other, and it turned out that Jacques referred me to them to work on Galileo with them because they thought I had some great ideas, because I've automated buildings thousands of miles away and made it so we can work on them and do these kinds of things. All right. Well, as it turns out, Avi and I had worked together already on several programs. We worked on an ABC special together. We worked on some podcasts together. We actually worked on another show together, but not together, separately, but together. So when Jacques Vallée made the introduction, Avi was like, "Oh, I know him. Yeah, have him talk to our team." So I did, and so there may be some place for me on there. I don't know. It would be nice, because I know I can help them automate, you know, their telescopes they're using to actually connect and get information, monitor, maintain. That's all good stuff, you know. And for those who wonder how I'm doing it, I actually write programs for Arduinos, and I use those microcontrollers, because I like making hardware do things that you know, you can make it do, you know. I'll show you, because I'm going to close down. Yeah, go ahead.
No way, JPL has tours, and so does Griffith Park Observatory. They keep it very clean, but every now and then I hear audience members try to push. But here, this is the conference where you can ask stuff like, did Jacques tell you he has the medal?
I've actually examined the medals personally.
Yes?
I held them. Yeah. I did it with another guy that you may have heard of, Douglas Trumbull. He was the guy who did 2001: A Space Odyssey with Stanley Kubrick. He did Close Encounters with Spielberg. He did Blade Runner.
Spielberg has the medal?
No, what I'm saying is I worked with Douglas Trumbull, who was the visual effects maven, Academy Award winner. He's passed away, but we were good friends for 10 years, and we worked together on lots of projects. And Doug, being the famous guy that he is, attracts the attention of people like that. He was into UFOs very much. That's how we met. And so we had a guy come up with those medals and sit down in our theater up there at the studio, and Doug and I were looking at these medals and handling them and checking them out. The reason they thought they were metals from other potential worlds was because the isotopes within the metals were all wrong for Earth-based materials. And that was done by an MIT lab. So I trust that MIT can kind of do it right, you know. And we had the guy from MIT there, he came. So that was pretty cool. You know, Doug used to call me his chief scientist. It was hilarious. You know, they'd be doing a movie, and I would mention how the spacecraft they want to do something in space couldn't operate that way because space doesn't work that way. And then their art director would say, well, that's how it's going to work. And then Doug would say, if he says it's not going to work, it's not going to work. You better listen to him. And they explained how, So he was a very, very humble guy and a wonderful man to work with. And I miss him greatly. He's a great guy.
Is it published? The determination of the content of the metal?
It was. And I know MIT published something because I read that paper. And they talked about the isotopic values and differences within the metals. I know the guy too that produced that, and I just can't think of his name. I'm not trying to hide it. I will tell you if I knew. I forget who it was. If I think of the name while we're talking, I'll let you know. Yeah.
So physically, was there anything unique about it as when you held it?
No, physically it looked like metal. It was very, very, boring. One piece was sort of a honeycomb structure. That was kind of cool. But I looked at that and I said, wow, this is a kind of a honeycomb structure, Doug. What do you think? He goes, yeah, it's kind of weird looking, And so it did have that appearance. And the guy from MIT said, yeah, this has a special isotope ratio in it that we don't find on Earth. And that's the thing that got my attention. If it's something you can't manufacture on Earth, and it's in there, that means it might have come from space, at the very least. But it was a manufactured material. It wasn't like a chunk of rock. And that also caught my attention. So you see? Yeah.
How do you know it was a manufactured material?
Question is, how do you know it was a manufactured material? Because it looked like a piece of manufactured metal, refined metal. It was not an ore, it was not a rock, it was actually a piece of shiny, refined metal. Okay, and you might have missed this, I said it was like a honeycomb structure. It was interlaced, it was interlocking objects, okay, in this one piece of metal. And I found that to be rather interesting, There was no ore. No, a rock is a rock, and that wouldn't excite me too much, to be fair. All right, let's see here now. All right, what we're going to do is we are going to park the telescope. We're going to, the moon's going to zip away here. I need to check that out. Hold on. Which way is park? I think, I know my screen very well, trust me, but when I actually see, it's hard to read sometimes. So let me try something here. Oh yeah. That's right. I think Avi, I don't know about Avi's connection to the material at all. I've actually never heard about that. One second, guys. I'm going to look at my screen here. I can't see where park is. I'm trying to see where the park is. I can't see where it is in here. But I will find it. All right, just one second here. I think this is it. There it is. Okay. Okay, we park the scope. And we will shut down this. Excuse me. Alright folks, I know that's been kind of a long night, crazy night, but this is the first live production we've ever done. This way anyway. Sure. And what I'm going to do now is I'm going to shut the observatory now that we've paused everything, got everything locked up. So that's what we're going to do next. Power is off. Now we're closing the building. All right, folks. Well, thank you very much for coming out here tonight. Those of you on the chat, it was very nice to see you. Daryl, I hope you heard everybody say hello to you tonight. I had them give you a shout out, and they all yelled, "Hello, Daryl." So that was very nice. And so we will be doing this again in Roswell at the end of the month, but we'll also be doing this back in Connecticut, well, starting as this cycle progresses through. But you guys have a good night out there, and I really look forward to seeing you all again. So have a good night, and thank you very much for coming, and I hope you will come back again. Thanks, everybody. And I know I didn't say hello to everybody in the chat. I am so sorry. I'm giving it my best shot. In any case, good night, folks, and we'll talk to you again.